Hello, my name is Jože Kurilc. I'm professor at the University of Ljubljana in Slovenia, and my professional field are finite elements. So I will present a special environment that is built on Mathematica. It's called AceFEM, that can be used to solve highly nonlinear finite element problems. So, dear colleagues, I will present some aspects of efficiency and accuracy of solution of large-scale finite element problems using AceFEM finite element environment. The work presented here was done by myself. I'm professor at the University of Ljubljana, and my co-workers, Blaž Hudobivnik and Urša Šolinc. So, what's motivation for the work I will present it here? Motivations are nonlinear problems that are emerging nowadays in industry, and that they have to be solved to move to the next level of like energy efficiency and to optimize our industrial products in a broader sense. To do that, we have to solve so-called M5 problems. And M5 problems is defined as a problem where we have multi-field problem like temperature deformations. We have multiscale problems, so we have to deal with the solution of the problem at several different scales. We have several interacting bodies or components. We might have several phases. And at the end, we have to do optimization, probably with respect to multi-objectives. So this, like right-hand side, we have a lot of demands. But on the right-hand side, on the left-hand side, we have demands. On the right-hand side, we have problems that are limiting our ability to solve the problems on the left-hand side. And those problems are mainly constitutive modeling. We don't actually have appropriate yet models to really model all those components. So it's still ongoing research to make a proper constitutive model. Finite element method, very, at least for solving nonlinear problems, is still in a state of infancy. So this is like a very simple example you can see here. Pressing down like a square, and if the nonlinearity is taken into account, 3 different types of elements would give 3 different solutions. Like this one is correct because this problem has also analytical solutions, so we know that this is correct. But some elements would give like this, it's called locking, which can eventually disappear if the element mesh gets denser, but some elements would give this solution. And this solution is clearly unphysical, and we can make mesh denser as much as we want. It will always be unphysical and incorrect solution. So if we are able to have a proper finite elements to model nonlinear behavior, we need also optimization, and we have to derive codes. There are 2 components that has to be present in our solution procedure nowadays if we really want to solve problems efficiently. And that's a primary analysis and sensitivity analysis. Everybody is talking basically about the primary analysis of the problems. Or most of the presentation seen here were about getting response of a kind of a system. But to really derive efficient algorithms to solve problems of M5 complexity, we also need sensitivity analysis. That means derivatives of the response so that we can make like gradient-based optimization, that we can linearize consistently multiscale problems, that we can make like efficient stochastic analysis. So all these algorithms can be made much more efficient if we have efficient sensitivity analysis, especially higher order. But this is a very complex problem when we have like M5 problem sensitivity. It's mostly done with the finite difference, which is very poorly defined, especially second order. And if we want to do it analytically, we actually need something like Mathematica to derive necessary terms. If you look, if you want to do these M5 problems automatically, we can look for two different goals of automation. Just to do automatically everything from ordinary or partial differential equation to the global solution. The next version of Mathematica 10 will have this kind of capability built in, done by Oliver, and I think it's very good work. There will be meshing inside. We are waiting for a long time for this kind of capability already, so we will be very happy to try them out. So we have this kind of capability inside now in the next version and dissolve. There are also alternatives around where everything can be done within single environment. But if you look at M5 problems, nonlinear problems, this is not an easy task. With the nonlinearity, the Pandora box is opening. And each problem has to be first derived. We need a way how to do automation of scientific research, not just automation of the solution itself. And that's about what I'm presenting, how to do that. Basically, if we want to do automation of scientific research, we are somehow allowed to do automation only of the tasks that are, in a sense, deterministic, not the ones where we can choose something. And basically, this is the differentiation and code optimization. Those things are pretty much deterministic, so we can do them automatically. And there is a system called ACE family, 3 components, AceGene, which can be used to generate numerical codes automatically, AceFEM, which is Mathematica-based finite element environment, and AceShare, which is a library of finite element codes that we can download from the internet. There are servers with a lot of dynamically linked files that can be automatically linked into the Mathematica and, in order to solve specific finite element problem. Why it's done in that way? That the finite elements codes are pre-generated and pre-compiled. Because when we're talking about nonlinear codes, they are usually quite huge, and it can take an hour or two to generate them if we want to have them efficient. So this is like a general scheme of the system. The essential components is the first is symbolic description, of course. We are using Mathematica to describe the problem itself. There is additional expressions, well control. When we deal with the nonlinear problems, the expressions tends to grow extremely rapidly. I will show an example later. So we need to control this expression as well. Then automatic differentiation is an essential part, and we have to have some interactive debugging of the code generated, otherwise we cannot do real research. So if you talk about automatic differentiation, what is inside AceFEM is so-called code-to-code transformation combined with the backward mode. We know we have 2 modes of automatic differentiation. One is very costly, it's a forward, and there is a backward mode where the gradient can be calculated practically for free. So if you want to make codes that are comparable with the manually written codes, this is the combination that has to be taken. Backward mode combined with the code-to-code transformation, not some kind of operator overloading stuff. I do simultaneous optimization of expressions by introducing auxiliary variables. And let's look at the first results. If you talk about efficiency of the generated codes, what code would be the most efficient? The code that has no loops, no calls to external subroutines, only formulas, one by one. So if we take a simple example, 2D plane strain nonlinear element, like hyperelastic, with 2 by 2 Gauss integration, and we generate this kind of code that evaluates tangent matrix and the residual of this type of the element, we get something like 22 kilobytes of the code, and like efficiency, let me say the efficiency of the code is 1. Where is the problem? If we would try to do that for 3D case with quadratic interpolation, that means 20-sided nodes with a 3 by 3 Gauss integration, the result will be 177,000 formulas. So we are stuck there. We cannot do actually 3D case. So we have to put some loops, like if you put numeric integration loop, the code size goes down, but efficiency is not, does not decrease significantly. And if you put another loop, like over the elements of the tangent matrix and the residual, maybe we get only 4 kilobytes of the codes and like drop down of 20% of efficiency for evaluation of the tangent and residual. So we can attack huge problems with this kind of approach without losing much of efficiency. This is an example which is a little bit more complex, multifield problem. It's a poroelastoplastic media, so it's like large deformations, fully coupled with the thermo and hydro mechanical fields. So if you just take mechanical problem itself, we get like, for this case, this is an example solved, so it's like a sponge pressed down, and the temperature is also calculated, and the pressure of the fluid is inside. So if we solve only mechanical problem, we get like 0.3 seconds. We add thermal problems for 0.45, and if we add all 3 unknown fields, it's like 0.6, the average time of calculating tangent and the residual of the problem. In a sense, it does not grow much. It's in a way, consequence of this backward mode of automatic differentiation. Oh, and this here, maybe a little bit of movie. So it's a kind of sponge clamped in the middle, and we are putting a fluid inside at the end, so it gets gross, and then we release the valve and goes back. So we have large deformations and pretty nonlinear response. Well, the second example I will present is design of structures as optimization problem. If you look at the engineering, I'm talking about civil engineering, so where the structures like this one are designed. The problem we have to solve is that we have like some initial design of the structure, like this. This is like frames with the bracings. Can be industrial building. And then we put a load on it. A load is a snow or maybe wind. And by increasing the load, we get a response curve. So increase the load, and we get response like displacement, or maybe we can put stress, whatever you want, on the x-axis. And the response curves are always nonlinear, because eventually the material gave up, it gets plastics, the cracks evolve, there might be instabilities. So we get some nonlinear responses, and by changing the design, we get different nonlinear responses. And the optimal one is that one that exactly matches the actual load, because we know the load, we don't know the structure. So we are looking for the structure that would give exactly prescribed response. The problem is that this response is highly nonlinear, and the results of a huge implicit system of equations. With the help of gradient-based optimization, we can formulate this kind of problem in mathematics quite easily, and this structure can be optimized into this by solving this optimization problem. So we're looking for the minimum volume of the structure that has exactly this response curve with some constraints. The constraints, of course, coming from the technology. There are some limitations how this can be formed from the point of technology. Of course, to run this example would be too much, so I will run a little bit smaller example. Okay. This can be optimized in real time. So it's a cantilever beam. Like here, it's a 2D problem. The one before was 3D, but it's the same one. We are looking for the shape of the beam that would give exactly this response curve. So by changing this shape, so we can parameterize this shape with several parameters, taking like linear or maybe quadratic interpolation along the x-axis, and by changing the parameters of the shape, we can search for the shape that has minimum volume, but at the same time, it has this response curve. Okay, I will run this optimization now, and we can look how it works. So those are iterations. I'm using simply find minimum in Mathematica. That works pretty well, actually. Not bad. Even when compared with some other packages available. So this optimization is going on. We have reached already quite a good solution. What is the good solution? The good solution is the one that would be completely red. That means the red means that we have reached plasticity, so that the material gave up. And at the same time, the curve has to reach 50. The 50 is prescribed load in this case. So these iterations are going on. Okay, it's done. So we got, like we can look at the results. So this is a shape. It might be more straight, but here is this technological constraint. I put that here has to be some minimum height of the beam at the end. Otherwise, it would be, the analytical solution is pure triangle, actually, if you would do this analytically. So this region is fully plastic, except of here where the constraints are active, and in the neutral axis, there are a little bit of unused material. So it's a pretty much optimal solution. And here are response curves put together for all the iterations of the optimization procedure. And this, the last one is here. And this is the objective function, which is combined with the volume, combined with some constraints where the interpoint constraints were put. And the volume, if you look at the volume of the structure, here are iterations and the volume of the structure, we can see that actually it's going up and down quite substantially from 3,000 to 5,000, and eventually it gets some optimal value. So we were able to optimize in a real time some pretty much nonlinear problem. We had actually 1, 2, 3, 4, 5 parameters, so the shape was parameterized by 5 parameters. Okay. The next problem I would like to show is multiscale. This is one of the components of M5 problem. It's a multiscale problem, so we have to solve the problem at several scales. One way to do that is to make a finite element mesh at different scales. So we have macro scale, and then we impose the deformation field from the macro scale on some micro scale, and by solving this micro problem, you get average stresses, which they go back up. And if everything is nonlinear, we get two nested nonlinear problems at the macro and micro scale, and we are jumping up and down. And to solve everything coherently together, we have to linearize that consistently, and that's the point where sensitivity analysis comes into the play. Okay, this is an example, pressing down. Each point here, Gauss point, is independently simulated as a continuum full of holes. So we have like this kind of microstructure. We can do this in real time, almost in real time for 2D problems, but when we go to 3D problem, there is a problem, because each micro problem, solution of each nonlinear micro problem, it's already extremely costly, even for a simple micro scale, like a problem like a beam. So with device, we used one of the functionality of Mathematica, ability to perform clustering of the data, to make a clusters of the micro problems based on the measure of the distance, which is a norm of the macro gradient. So we were able to reduce the 8,000 micro problems into 20 micro problems. And we got some kind of clusters of these micro problems. And with this sense, we can really reduce the computational cost. And the last things I will present is isogeometric formulations. We know that somehow the new tools in the armory of the numerical methods are emerging like constantly, and maybe isogeometric formulations are the latest weapon in this armory. What are the isogeometric formulations? We know that the standard finite elements, they have at least two sources of errors, discretization errors, of the discretization of the geometry and discretization of the unknown fields themselves. So we want to eliminate one of those errors, and the isogeometric formulation is the way to do that. So we describe the actual geometry by using some higher order functions like splines or NURBS, taken directly from the CID representation of the object we want to model. Eventually, we end up with pretty much the same structure of the problem as with the finite elements. It's just that this formulation of the shape functions is quite more complex. Also, the remeshing becomes quite complex. Okay, but even in that case, it's interesting that the code optimization actually for isogeometric elements give the same efficiency as for simple elements. It was it was quite surprising fact for the people that are working on isogeometric formulations. And this isogeometric formulation were used at the end to optimize the one problem. It's called surface wrinkling. If you look at in the nature, octopus or maybe chameleon, they have a special skin that can wrinkle to mimic the surrounding. So there are certain area where there is a need to mimic that with some kind of mechanism. And we have devised this kind of multi-layer model with the little wires on that can shrink, and the pattern of these wires can be controlled as a parameter of the problem in order to get some prescribed surface wrinkling. And those are results. Like we can get different types of surface wrinkling by changing the pattern of stretches of the wires imposed on the surface of this multi-layer skin. by imposing the continuity, the periodicity, actually the little piece represents the true surface that is infinitely wrinkled. Okay, that was all of the latest development in AceFEM. Thank you.